Hello, in this video we will discuss about time-based waveforms. Generating time-based waveforms. Coming to a time-based signal, any signal which varies linearly with time is called time-based signal. An example is a sawtooth waveform which varies linearly with time. After a certain time period, it drops down to initial value 0. Again, it varies linearly with time, drop down to 0. And any circuit which generates such type of time-based waveform, which generates sawtooth model waveforms, are called time-based generators. And coming to the velocity, horizontal velocity of the waveform should be a constant. For example, when we apply a voltage signal on the deflection plates in CRO, a beam will be scanned on the screen from one end to the other end, and it will produce an output waveform that is called time-based waveform. Whenever we apply a voltage signal on the deflection plates in the CRO, it will allow a beam to trace, a beam to scan. A beam will be swept horizontally on the screen from one end to the other end. This will produce an output waveform that is called time-based waveform. Any circuit which generates such type of time-based waveform are called sweep circuits. Those waveforms are also called sweep waveforms. Coming to the features of time-based signal. This is original sawtooth waveform where the amplitude will vary linearly and then drops down to 0. Amplitude varies linearly, drop down to 0. And the time for which the amplitude varies linearly is the time period of the waveform, capital T. Coming to sweep waveform, this is the actual waveform, but in the circuits it will be generated slightly like this, and the portion where the waveform varies linearly is called sweep time. The time for which waveform varies linearly is called sweep time. And after reaching the maximum time, it drops down to the initial value. The time taken to drop down from the maximum to initial 0 value is called restoration time. From the beginning, coming back to this 0 value is called restoration time, and the total time is the sum of sweep time and the restoration time. And here, whenever we apply a signal on the deflection plates, beam will be swept on the screen. When the beam is swept from one end to other end, it is otherwise called as scanning, and in the forward direction it can be called as trace of the signal. When the beam is sweeping from the left to right, for example, if the trace is beam sweeping from right to left, retrace will be the beam will be sweeping from up in the opposite direction. If it is left to right, this will be right to left, and this retrace is otherwise called as flyback. And the time for which linearly variation in the waveform occurs, that is called sweep time, and the time taken to restore back to the initial value is called restoration time. Other name is flyback time or retrace time. Coming to the type of time-based generators, whenever the circuit generates a voltage type of waveform at the output, it is called voltage time-based generators. If the output generated in the circuit is current signal, then it is called current time-based generators. Coming to the application of time-based generators, it is used in televisions, radars, time measurements and time modulations. Also, the working of time-based generators can be referred in the link specified below in the slide. We will go with voltage time-based generators. This is a simple voltage time-based generators. It is designed using the components resistor and capacitor and a transistor followed with another resistor R1. Vi is the input and V0 is the output. VCC is the supply voltage. This capacitor will try to charge to VCC through the resistor R2, and the capacitor will try to discharge through the transistor and R1. Whenever This circuit will produce an output waveform which varies linearly with time, and hence it is called voltage time-based generators, because output waveform is going to be a voltage waveform. If we give an input signal in this fashion, whenever there is a trigger, whenever there is a pulse, then it flows into the base of the transistor. Transistor will come to on state. Whenever transistor is in on state, it will give a low resistance path to the capacitor for discharging. So whenever pulse is applied at the input, capacitor will discharge through the low resistance path through Q transistor and R1. Q and R1 is the path for discharge for the capacitor. It will discharge up to the level VCE saturation, and then once the pulse is ended and the transistor comes to off state, at the end of the pulse, transistor will come to off state, open circuit, and the capacitor will try to charge. In this case, capacitor will try to charge up to VCC, which is the maximum voltage. The path for capacitor charging is through R2 resistor up to VCC, and this is the capacitor charging taking place. It is trying to charge up to VCC, and the output waveform for this portion is given by VCC into 1 minus e power minus t by RC. VCC is the supply voltage, V0 is the instantaneous output voltage captured from the output of the circuit, and t is the time taken for charging, RC is the time constant or elements in the circuit. There are different types of time-based waveforms generation methods. There are different types or methods to generate the time-based waveforms. They are exponential charging method, constant current charging method, Miller circuit, bootstrap circuit, and then compensating circuits, inductor circuits. In exponential charging, we will be taking a capacitor which will charge to a voltage level V, which is as small as compared to the charging level of the capacitor. In constant current charging, we will charge the capacitor using a constant current source, and at the output we are going to get a ramp type of waveform. In the Miller circuit, we will give a step input, and using an integrator circuit which is Miller, it will be converted to a ramp waveform. So step waveform will be converted to ramp waveform using integrator in Miller circuit. In bootstrap circuit, we will try to give constant current passing through the capacitor, and this can be made possible by maintaining constant voltage at the resistor. Thereby a ramp type waveform is generated at the output of bootstrap circuit. In order to maintain linearity in Miller circuit and bootstrap circuit, we are going for compensating circuit, and inductor circuit is one of the example for compensating circuit. We will go with exponential voltage sweep circuit. And output is voltage waveform, so it can be called as exponential voltage sweep circuit. This is a simple circuit designed using resistor, capacitor, a switch, and voltage source V. Before time t equal to 0, switch will be in closed condition, and as it is short circuit, output voltage is 0. At t less than 0, switch is in closed condition, output is 0. And at t equal to 0, switch is kept in open condition, and thereby capacitor charges to the voltage level V through the resistor R. Output is taken across capacitor, and at t equal to 0, capacitor starts charging up to the voltage level V, it will try to charge. So after t equal to 0, the capacitor voltage is trying to charge up to voltage level V. But at time Ts, switch will be kept closed. Once switch is closed, again short circuit is formed here, and capacitor voltage drops down to 0. If at all switch is closed at Ts, then this voltage will stop here and it will drop down to 0. If we consider this portion, we have to check how much linear the waveform is generated. how much linear the slope of the waveform we have to check for linearity of the waveform being generated. If switch is not closed at Ts, the capacitor will charge up to maximum level V. So this entire portion of the waveform output voltage can be represented as V into 1 minus e power minus t by Rc. And here R and C define the time constants. Ts is the time for which a switch is kept open, and the slope linearity is defined by a factor called sweep error, and the sweep error is nothing but ratio of Vs by V. At Ts, at time Ts, capacitor charge is Vs voltage level. At Ts, capacitor charge is Vs voltage level. So now we are making a comparison of this Vs and V, and hence this Vs divided by V represents the linearity or the slope of the waveform for the period where switch is kept open. If at all Ts, switch is closed. If at all at Ts, switch is closed, this portion we are analyzing the linearity by the slope Vs by V. And for the error to be small and the waveform to be more linear, we should keep time constant high, and this time for which switch is open should be very small. If this time is very small, we will get more linear waveform, and time constant should be maintained high, Rc should be maintained high. And for checking linearity of the waveform generated through sweep circuits, we have some measures: sweep error, displacement error, and transmission error, and they are given by these mathematical equations which we will derive ahead. Coming to the errors in the waveform which are generated by sweep circuits, we will determine whether the waveform is linear or not. These are the measures: sweep error, displacement error, and transmission error. Coming to sweep error, this is the waveform we are going to generate in exponential sweep circuit, and this is the equation, output equation, V into 1 minus e power minus t by Rc. And for this equation we have to find the slope at t equal to 0 and t equal to Ts. This is the initial point where switch is open, final point where switch is open. We are finding slope at these 2 points, and the difference divided by the initial slope. Switch is kept open between this time duration t equal to 0 and t equal to Ts. So initial slope minus final slope divided by initial slope when the switch is kept open entirely. This total analysis is when switch is kept open, and this is said to be slope error or sweep error in the waveform. Similarly, displacement error. This is the actual sweep, the waveform or the capacitor charge actual sweep going to happen, and this is the linear sweep. This is the linear sweep ramp type waveform. Coming to displacement error, difference between actual sweep to linear sweep divided by the maximum amplitude at the end of Ts seconds. Switch is kept open only for Ts seconds. At the end of Ts seconds, what is the sweep amplitude? And that is said to be displacement error. Numerator is actual sweep minus linear sweep divided by the amplitude at the end of Ts, sweep amplitude at the end of Ts. This is displacement error. Coming to transmission error, we will try to send a linear waveform, ramp type waveform, but during transmission it will get slightly distorted. So this is the linear waveform we are trying to send, and during transmission it is slightly getting distorted. This is the transmitted waveform, output waveform. So our input is this ramp type waveform, output is this Vs. So difference between input and the output divided by input waveform is the transmission error. So input ramp distorted waveform output divided by the input waveform at the end of Ts will be transmission error. Based on this discussion, we will slightly see a few questions. First question, if the spot is required to be swept linearly as a function of time in a CRO, ideally the signal that is to be applied between X deflecting plates is a sawtooth waveform. So in order to have the beam sweep on the screen, we should apply sawtooth waveform for generating sweep waveforms, time-based sweep waveforms. Second question, if in the output of time-based generator voltage varies linearly till Ts, then the time-based generator is called voltage sweep generator. Output is voltage varies linearly, so the circuit is voltage sweep generator. Next question, the time-based generator which uses the principle of electrostatic deflection is called CRO. CRO uses electrostatic deflection. The errors ES, ED and ET define the deviations from linearity in the circuit. These are the measures for analyzing slope or linearity of the waveform generated. Next question, the error that gives the ratio of difference of slope at the beginning and at the end of the sweep to the initial slope is known as slope error or sweep error. When the switch is kept open, initial slope minus final slope divided by initial slope, that is slope error. Next question, the error that specifies the ratio of maximum difference in voltage between the practical sweep and the linear sweep to the sweep amplitude is known as displacement error. The second thing we have seen, error, it is actual sweep minus linear sweep divided by maximum amplitude at the end of Ts, it is displacement error. Next question, the error that gives the ratio of difference in amplitude of a linear sweep to the sweep amplitude in the output to the amplitude of the linear sweep. Our input waveform is linear waveform and output is distorted waveform. So difference between input and output divided by amplitude of input is termed as transmission error. The interrelationship between ES, ED, ET is given as ES is nothing but Ts by RC, ET is nothing but Ts by 4 RC, ET is nothing but Ts by 2 RC and ED is nothing but Ts by 8 RC. And based on this, the answer is ED equal to 1 divided by 8 ES, which is equal to 1 by 4 ET. ET is Ts by 2 RC, ES is Ts by RC, ED is Ts by 8 RC, and hence this relation holds good. Application of a voltage time-based generator can generally be seen in a measuring instrument like CRO. In CRO, we can see voltage time-based generator waveforms. The principle behind the deflection of electronic beam in a CRO employing a voltage sweep generator is called electrostatic deflection. Last question. In a simple exponential sweep generator, if the time constant of the circuit is 1000 microseconds and the sweep duration is 100 microseconds, then the slope error would be, formula for slope error is Ts by RC. So Ts is sweep duration 100, RC is time constant 1000, both are microseconds. So 100 by 1000 is 1 by 10. In percentage means you have to multiply with 100. 1 by 10 into 100, if you multiply, it becomes 10%. Thank you.